These first set of practice problems for chapter 11 deal with gases that have changed conditions. So they have an initial set of conditions and they have a final set of conditions. So let's look at number one. Number one, they tell us we have initial, our balloon is at 1.05 atmospheres, and that it has a volume of 475 milliliters. And then its second set or final set of conditions, it is compressed to 88.3 milliliters, and we want to know what is the pressure. Okay, so for this problem, it doesn't say it, but we can assume that the temperature and that the number of moles of gas have stayed constant. So we're looking at the relationship between pressure and volume. So we're looking at how pressure changes when volume changes. So we're going to use Boyle's law. P1V1 equals P2V2. My dogs seem to agree that Boyle's law is definitely the way to go. So 1.05 atmospheres times 475 milliliters equals P2 times 88.3 milliliters. So we're just substituting into our formula all the things we know, and we're going to solve for P2. So notice I didn't change my units from milliliters. It doesn't matter so long as they're the same. So this is in milliliters and this is in milliliters. So we don't have to change from that. If this was, say, given in liters and this was in milliliters, we just need the two units to be the same because they are going to cancel out. Okay, so P2 will be the 1.05 atmospheres times 475 milliliters divided by 88.3 milliliters. So our milliliters cancel and we can solve for pressure. Okay, so we'll put this in the calculator. Okay, so you might not be able to see this because this calculator is probably older than everyone watching this show. So 1.05 times 475 divided by 88.3. This gives us a pressure of 5.65 atmospheres. Okay, so just like Boyle's law tells us, when the volume goes down, the pressure will go up. So we had a decrease in volume and an increase in pressure there. Okay, let's look at number two. Number two, we have a balloon initially at 52 degrees Celsius and 1.85 liters, cooled to negative 17 degrees. So what is the volume of the balloon? Okay, so more initial and final sets of conditions. So we'll go initial, final. So initially we have 52 degrees Celsius, and initially we have 1.85 liters. In our final, we have a final temperature is negative 17 degrees Celsius. So with gas laws, we have to use absolute temperature. So we need to change these Celsius into Kelvin. So a reminder, temperature in Kelvin equals temperature in degrees Celsius plus 273.15. Okay, so I'm going to convert these two to Kelvin. So 52 plus 273 gives us 325 Kelvin. And then negative 17 plus 273 gives us 256 Kelvin. Okay, so we are solving for V2. So we want to know what the volume of this gas will be after cooling. Okay, so scroll up a little here. Okay, so this is looking at the relationship between temperature and volume. So this is Charles' law. So we know that V1 over T1 equals V2 over T2. Okay, so we'll substitute in. So 1.85 liter over 325 Kelvin equals V2 over 256 Kelvin. Okay, so I'm going to solve for V2. So V2 multiply over 256 Kelvin times 1.85 liters divided by 325 Kelvin. Okay, so our Kelvins cancel and we're solving for our volume. So 256 times 1.85 divided by 325. So we get we'll call it 46 liters. So in this case, we decrease the temperature and our volume of gas decrease. So this is consistent with Charles' law, where we know they are directly proportional, and a decrease in one will result in the decrease of the other. So 1.46 liters. Okay, our next one, number 3. So in number 3, we have a lot of things going on. Weather balloon at 1.5 atmospheres and 2 liters and 30 degrees Celsius, released into the atmosphere, and then measurements were taken, and the balloon is now at 1 liter at a temperature of -5 degrees Celsius. So what is the pressure? So same thing, we have initial and we have final. So we have 2 sets of conditions for this balloon. So initially we have 1.5 atmosphere. Initially we have 2.0 liters. And initially we have 30 degrees Celsius. And then our final, we have 1 liter, and we have -5 degrees Celsius. Okay, so, and we are solving for the pressure in the upper atmosphere. So we are looking at the change of pressure, volume, and temperature all at the same time, where only moles of gas is constant. So this is going to be the combined gas law. So for the combined gas law, P1 V1 over T1 equals P2 V2 over T2. Okay, so before we get in there, let's do a couple quick temperature conversions. So 30 plus 273 gives us 303 so now since we have a measurement to the tenths, we'll keep this to the tenths. So 303.2 Kelvin. So now we have 273 plus -5 gives us 268.2 Kelvin. Okay, so here's our 2 temperatures. So we're going to substitute everything in. So our pressure, so we have 1.5 atmospheres, and we have 2 liters, and we have 303.2 Kelvin equals, so now on this side, our P2 we are solving for, so we'll have P2 times 1 liter divided by 268.2 Kelvin. Okay, so to solve, I'm going to rearrange for P2. So P2 equals 1.5 atmospheres times 2.0 liters. So I'm going to multiply this over times 268.2 Kelvin divided by 303.2 Kelvin. And then to get just P2, divide over by the 1 liter. Okay, so when we do this, our liters cancels and our Kelvin cancels, and we're just left with our atmosphere units here. So we end up with 1.5 times 2 times 268.2 divided by our 303.2 and our 1 liter, which gives us 2.65 atmospheres. So our final pressure inside of our weather balloon is 2.65 atmospheres. So we had a couple of things going on here. So first of all, our volume decreased and our temperature also decreased. So we had kind of 2 conflicting things going on there. The decrease in volume sort of indicated that the pressure should increase, but also the decrease in temperature sort of suggested the pressure should decrease. Turns out that the more sort of drastic drop in volume resulted in that particular thing winning out, and we got an increase in pressure. Okay, so our last problem. Problem number 4. Okay, so we have a gas that has 0.567 moles and a volume of 3.7 liters. And we want to know, what will the volume of the gas be if we add an additional 0.122 moles? So again, we have initial and final. So initially we know that we have 0.567 mole, and that has a volume of 3.7 liters. And then over here, it says we are adding 0.122 moles. So our moles here is going to be 0.567 plus 0.122. So we are adding more moles of gas into the balloon and V2. Okay, so this moles and liters, the relationship there, that's Avogadro's law. So Avogadro's law states that the volume of a gas is directly proportional to the moles. So since we've increased the moles of gas when we solve, we should see an increase in the volume of gas. Okay, so let's go ahead and add what we have here, 0.567 plus 0.122. So now in the balloon we have a total of 0.689 moles of gas. Okay, now we can use Avogadro's law. V1 over N1 equals V2 over N2, and we can substitute in. So we have 3.7 liters over 0.567 mole equals V2 over 0.689 moles. Okay, so we're going to solve for V2. So V2 is going to be 3.7 liters times 0.689 moles divided by 0.567 moles. Okay, so 3.7 times 0.689 divided by 0.567 will give us 4.5 liters of gas. So this was our final volume of gas after adding more moles. So again, for these types of problems in this video, we had an initial set of conditions and a final set of conditions. So we were using Boyle's law, Charles' law, we were using Avogadro's law and the combined gas law. The only one we didn't see here is Gay-Lussac's law, but you could use Gay-Lussac's law if you had pressure and temperature as your two variables, and again you had initial set of conditions and final. So that's when you use these types of laws, when you have your conditions are changing. You have initial temperature or pressure and then it's different at the end of the problem.